Welcome and good morning. I hereby open the public meeting of the Doctorate Committee of Tristan Tomelin. The meeting today is in hybrid form with some of the committee members and people in the audience joining us online, and I would like to welcome them as well. I kindly request the doctoral candidate and his seconds to come forward and take their place behind the lectern. I'll give the word to the promotor, Professor Perniski, to ask the first question to the candidate.
Geachte voorzitter, bedankt. Geachte promovendus, please tell us in the next 10 minutes about your PhD research.
Bedankt voor uw vraag. To build great things, we need proper tools. If the tools at our disposal are inadequate, then the things we make with them tend to be of poor quality as well. Many great things have been made possible by reinforcement learning. It all starts with theory, of course, but what lies in the middle of it? Well, many things, definitely. But for sure, I can say that having access to these proper tools is a key ingredient. But how does that relate to reinforcement learning? What does that mean? What are these tools for RL? So imagine we want to train this robot to walk in the real world by just random exploration. So not only would it repeatedly break itself and everything around it, but it would also take a very long time. So instead, we could do this in a simulation environment, which would be much faster and cheaper. So simulation environments don't always attempt to replicate reality. Sometimes we want to study simpler problems in isolation. Take this maze, for example. In an RL environment, we generally have what we call an agent who ought to set out some goal. It can take actions to do so, and if all goes well and it takes the right actions, it gets a reward. So these game-like settings have long served as environments for reinforcement learning. The Atari games have been used as testing grounds for decades and still remain relevant today. Dota and StarCraft pulled waves of attention when AI agents beat the world champions. So existing settings, however, don't cover any problem we want to study. Those need environments of their own. So this is what I set out to do in my thesis, to build environments for reinforcement learning research. They should be fast to run and tell us something about why methods fail and why they succeed. I focus on these three domains, which are generalization, continual learning, and safe reinforcement learning. So let's zoom in on the first one. So what does it mean to generalize? So say, for example, you want to get good at tennis. You train, you do a good job, and you get good at the game. And now one day you show up on the courts, and you have to play with a different color of balls. And suddenly you find yourself missing every single shot. So this would be quite an unlikely scenario for us humans, but AI agents, on the other hand, would be rather likely. Not only in tennis, but say, for example, we train this agent to shoot some enemies in this video game, and it's doing a pretty decent job. But the moment we change the textures of the floor and walls, it suddenly has no clue what is going on anymore. So generalization matters because we wouldn't want to train these agents over and over again because it's costly and time-consuming. Instead, we want them to be robust to these perturbations. So motivated by this, I changed environments of this video game by, for instance, changing the size of the items or changing the textures around, or even combining these modifications to reach higher levels of difficulty. And then we can use these environments to train reinforcement learning agents and evaluate how well they do in these unseen settings. And the benchmark provides tools to assess how well agents generalize when learning from pixel observations in these 3D environments. And researchers can use this to develop methods that generalize better. Instead of directly generalizing, sometimes our setting allows for extra training when we encounter a new task. Then we arrive at the realm of continual reinforcement learning, which I address in chapters 4 and 5 of my thesis. So what does continual mean? So let's go back to our tennis example. You're good at tennis, but now the weather gets cold outside, so you move indoors and pick up table tennis. So now what happens is that when you train the table tennis and you get better, your skill at regular tennis decreases because there's some interference between the technique that you use. So in continual learning, this is known as catastrophic forgetting. This is something we want our agents to avoid, or at least mitigate to some extent. On the positive side, you can also leverage the knowledge you've gained from the past tasks you've learned and train a new task very fast, very efficiently. So this would be known as knowledge transfer forward. This is something preferable. So in a continual learning sequence, we always train on the most recent task, and ultimately we want to perform well on all of them. But to assess algorithms in these metrics, we again need simulation environments, which are particularly lacking in the 3D domain. So again, I use this video game to create continual learning sequences this time, which we can use to measure forgetting, forward transfer, plasticity, and much more. For instance, for forgetting, we can see how this method does a good job at learning the first task, the blue curve, but the moment it starts learning the second one, the green curve, it immediately forgets the first one. And this repeats to the end of the task sequence. Another method, for instance, does a very good job at this, almost displaying no forgetting and having perfect retention. So a key design choice here is not to make the problem too easy or hard, so we can distinguish how well these methods compare and rank to one another and form a sort of a leaderboard. So apart from just leaderboards, we can also use these benchmarks to analyze what is happening underneath. So for instance, the agent is allowed to choose between these 12 actions. And for instance, we can visualize which are the actions that it performs throughout training on each individual task. And also we can see what happens during evaluation when we evaluate it on the first task while it trains on future ones. And in this case, it does a very good job at maintaining this preference it had during the training on the task. So sometimes we're not dealing with one agent, but multiple. And they also need to collaborate with one another. So the field of multi-agent systems has grown very prevalent, but there hasn't been much focus on the continual learning perspective. So in chapter 5, I use a simplified grid-based version of this popular cooking game and create Meal to research how collaborative behaviors of agents transfer across very long task sequences. So Meal is the first benchmark to combine these two fields of continual and multi-agent. So I create two types of sequences. In the first one, the agents have to adapt to different kitchen layouts. And in the second one, a single chef has to continually adapt to collaborate with different partners. So thanks to the very efficient simulation of these environments, we can feasibly scale up the number of tasks to up to 100, something that has not been done in continual lateral research before. So this matters because with short sequences, some patterns may not emerge yet. To control the difficulty, I increased the size of the kitchens, and in only a few hours of training, we can measure continual learning capabilities across 100 tasks. We can observe what effect this has on forgetting, and we can also assess how a different number of agents impacts performance. In the last two chapters of my thesis, the focus is on safe or constrained reinforcement learning. So what makes it constrained? Going back to our tennis example, imagine you are playing a match, but unfortunately, you slip, fall, and injure your ankle. You still have your original goal of scoring as many points as possible and winning the match, but now you're acting in this kind of a constrained setting where there's this associated cost with taking certain actions, for instance, too sudden or fast movements that might further injure your ankle. And there's this certain threshold beyond which you're no longer able to continue the match. So to study safe RL, we need environments built around such constraints. And in particular, there are not too many when learning from visual inputs. So this is what I address in chapter 6. As before, each environment prompts the agent to achieve some objective, but now it has to avoid a certain behavior. So roughly mimicking the real world, this opens new lines of research for studying perception, navigation, and much more. And in chapter 7, I extend this design to a physics simulation environment. So here, the core focus is being on very computationally efficient, and it scales orders of magnitude faster than previous benchmarks. So these environments we can then use to evaluate how different safe reinforcement learning methods perform. We can, for instance, see what kind of behavior correlates with poor performance and what successfully solving the task looks like. A key design decision here is to have this direct trade-off between performance and safety. So for instance, if we were to loosen the safety bound, then the agent acquires a more reckless behavior and yielding more reward. Whereas if we tighten this bound, then we get a more conservative approach, and it requires a sacrifice of reward. So while the cost bound shapes how the agent performs, what the agent can see shapes what it can learn. So to study perception within the benchmark, I include settings where the agent receives segmented observations or has access to the depth information. And it turns out that both of these improve learning and make the task easier. An agent's movement can also tell us about what it has learned. So I analyze this in a top-down view of the environment by recording the agent's position throughout the training, and then the benchmark turns this into a heat map. And then if we juxtapose this with the training curves, we can see how the movement and navigation correlate with the actual quantitative performance. So to finally answer the question of the promoter, during my PhD, I built these tools as layers of evaluation for reinforcement learning research. The settings I addressed had no standardized environments, so results were hard to compare and existing simulators were slow to run. Apart from serving as leaderboards, these benchmarks now help us not just to see whether a method fails, but where and why. experiments that would have taken days to run now only take a couple of hours. So we can be more frugal with the resources that we use. And we can ask new questions that previously were out of reach or too expensive to answer, as benchmarks do not only measure progress, but they shape it. Thank you very much.
Thank you. Professor Pechnicki, are you satisfied?
I'm fully satisfied, thank you.
Thank you. Eindhoven University of Technology very much values the presence of experts from outside our own university in doctorate committees. And today we are privileged to welcome Professor Piotr Milosz of the University of Warsaw, Professor Jun Wang of the University College in London, and Professor Mark Wienans from Maastricht University. The time investment is quite significant, both for reviewing the thesis and attending the defense, and we are particularly grateful to them for their efforts. I would now like to give the word to Professor Wienans.
Geachte voorzitter, thank you for your nice words and introducing me. So, geachte promovendus, dear candidate, I've read your thesis with much pleasure, as it discusses a rather interesting topic of developing better benchmarks for reinforcement learning. And especially your first chapter is a great read, which I would always give to my students as well, how to set up a benchmark and what are the problems there. And many of your results have been published in strong venues. I especially liked how well the thesis is structured, because every time you started with a nice table of the new aspects that you would introduce it compared to other benchmarks. My compliments, which I would like to extend to your supervisors. Of course, I still have a couple of questions. Now, you're using Wisdom as one of the main baselines for your benchmarks. And you also argue, well, it is 3D and it has embodied view and it's also nice for robotics applications. Also, you argue it's also lightweight engine, which also makes it nice for reinforcement learning algorithms to sample a lot. So you can actually learn a lot. Now, this is a game from the 90s that I still played in the 90s. Yes, I'm that old. Which means that also the so-called fidelity is limited. And the fidelity is basically the physics engine, but also the level of detail. The world in Doom is still quite blocky. And we also know when the environments become more sophisticated, also AI systems start to break. There are also other alternatives like Quake, late 90s, or even the Unreal Engine. So I was wondering, because these engines' fidelity is much higher, why did you still go for Wisdom? And then I was also wondering, what is the impact of using Wisdom with a limited fidelity on your results? How trustworthy are they?
Hooggeleerde opponent, bedankt voor uw vraag. I think this is a very good point to address. And there's many ways to go about this. I think the core question is, what are we trying to achieve with using the environment in the first place? So as I described in chapter 2, there's this notion of our goal is to achieve some means in the real world, then we would want to create like a digital twin, something very close to reality. But if we want to study something in isolation, as I mentioned, something more simpler, then, well, we still have researchers doing RL on the more theoretical side who use very simplistic environments with maybe 4 states and 2 actions to really pinpoint something crucial. So here we come where we kind of land somewhere in the middle. Where on the spectrum is not exactly clear, but so that kind of motivates why we would want these semi-realistic environments. Now, the question with why Doom? Well, one answer would be that it was already somewhat adopted to a certain degree by the community. It started in 2016, where it was made. There were some competitions on it a few years later. So there is a certain benefit of people being familiar with an environment, and they already know how it works. Like if we take the Atari games or the Mujako environments, then RL researchers, if they see the image on the poster, they immediately know what the problem is that it's trying to solve. So the familiarity aspect is one crucial thing. Why not Quake? Quake was also used for the DeepMind Lab benchmark. So it's also a good candidate, I suppose. But with Wisdom, it was, the lightweight aspect of it made very fast and efficient to run. And and train on.
Yeah. I like your answer because you say this is spectrum. Huh? So on the one hand, you would like to keep it as lightweight as possible. On the other hand, you would still have a kind of semi-realistic environment to a certain extent. Now, when I started as a young assistant professor somewhere in the 2000s, and I went to Game AI conference, they always use games from the 80s and the 90s, which I understood because they don't take that much computing resources. Now, 15 years later, we as a community, what are we still doing? We're using games from the 80s and the 90s. Of course, you could say these games are great, but when are we start to move to have more sophisticated games? So when, and I'm looking to figure out when, what is the trade-off between realism and also being able to do better AI? Should we take games from 40 years ago? Should we take games from 30 years ago? Should we say, well, a game shouldn't be older than 20 years ago? Is there a kind of heuristic for that?
Mm-hmm. Yeah, it's a good point. I think there's two ways I would like to answer this. Well, one is that essentially the selection of the game, it's somewhat it relates to the way how well it correlates to reality in the sense that it's not really 3D, right?
Yeah.
The physics engines does not support it.
Yeah.
It's like 2.5D in a sense. Yeah. But the question is what does it show to the agent? What does the agent observe? From the perspective of the agent, it still sort of mimics if we would have some real world applications where there's a household robot that needs to clean dishes or something. There's this similar perspective of this egocentric perception from an embodied perspective. And there are some objects in the environment, and as you take a step forward, something in the surrounding area changes. And if you mentioned why shouldn't we use newer ones, then, well, we already are. There are many, in recent years, there have been many works on these generalist agents that play Red Dead Redemption 2 or something more recent. But these are big frontier labs that have the capabilities and computational resources to run this. So a big focus of the thesis was also to lower the barrier of entry for maybe researchers who want to run experiments on their laptop. They don't have resources to use 3H100s in parallel to train something. Okay. So that is a key sort of line throughout the many chapters.
Geachte voorzitter, do I still have time?
There's time for a final brief question.
Final brief question. Of course, at the beginning, you also showed StarCraft and real-time strategy games. So I was wondering in how far can some of your ideas quite easy being transferred when I would like to set a better benchmark for real-time strategy games like Micro RTS or StarCraft.
So you mean the methods I designed?
Yeah. Speaking at a higher level. So which lessons have you learned from your benchmarks that you could actually say you could also apply to real-time strategy games for making better benchmarks?
To apply to real-time strategy games. I would say in terms of designing the environments, one key thing is to make the problem somewhat easy and somewhat hard, depending on what we're trying to solve. With real-time strategy, I think it is more difficult to pinpoint smaller scenarios. I think the core example is the multi-agent, the SMAC, the multi-agent SMAC environment, where this is done. So this is like one example where the whole game is taken kind of into parts, and then we focus on something more specific. So I think the one core thing is to sort of have sufficient reward shaping, not to make something too complex to solve. Otherwise, if all methods just hit a flat zero in terms of performance, we couldn't really say much about comparing them. So I think those are the few things I would focus on.
Thank you. I'm satisfied.
Thank you very much, Professor Wienans. I would then like to invite Professor Milos to continue the opposition.
Haidar, can you hear me? Okay, cool. Dear candidate, so I like a lot the focus of your thesis. I think that making benchmarks is a really important task because it shapes how the community is evolving and thinking. And I have maybe kind of an open question at first. So it is so, and two of your benchmarks, and there is meaning comment Milius studied the intersection of continual learning and reinforcement learning. And my question is, what are specific challenges for reinforcement learning methods when for the CL methods when they are applied in the RL regime? If you can discuss this shortly, and I might have some follow-up questions after.
Yes. Hooggeleerde opponent, bedankt voor uw vraag. So, if we think about typical continual learning, like let's say supervised continual learning, then it's more about, there's not this notion of tasks, but it's more about classes or domains. For instance, we learn to identify cats and dogs from photos, and then we have a new animal, and then we extend to this. So with reinforcement learning, we get this notion of a task. So we don't have, at least in the online setting, we don't have the data beforehand, right? In online RL, as the agent trains, it also gathers the data that it learns from. So then there's also the question of exploration that really comes into play here. And this sort of also correlates strongly with the transfer aspect. So I think in terms of forgetting, the issue is somewhat similar. But the key crux is now that if we have already learned a task, we've already gathered some data. Now the question is, if we transfer to learning a new task, then can we use something from the task we learned to improve the exploration at the beginning of the next task that we start to learn, right? So this whole exploration aspect wouldn't be the case in supervised learning or another case. So with RL agents, I think one of the key ingredients is this question of how can we explore better and leverage the knowledge that we've already gained.
Mm-hmm. And how about, so this was actually my second question that I prepared, but it goes smoothly with this one. So how, because in so to speak, this standard CL, we can have some settings when the tasks are, the boundaries between tasks are either like rigid or kind of maybe smooth. And here that boundaries don't exist in any sense, because we like that task is changing all the time. So can we say benefit also within the same task from the continual learning methods? So say, can we like positively transfer something from the, like, say, the first part of the task to the second part?
Okay, thank you for the question. So indeed, it of course depends what type of continual learning problem we're solving. So mainly in the benchmarks I created, I focused on the setting where the boundaries between tasks are very rough, and the task itself is more or less unchangeable during the time the agent interacts with it. Now, if we think about settings where there's more of a continual drift and there are no clear boundaries, then indeed we might still have a notion of a task, but also, like, you know, if we think about some real world examples. Even if we have different tasks of a robot picking cucumbers in a greenhouse and then it switches to picking tomatoes in a greenhouse, then, well, the sensors break down, there's, I don't know, different weather outside. So even during the same task, there's still there's some drift within what it can observe. So indeed, then this becomes a bit of an issue. And then can we somehow leverage something from it? Well, I suppose in this sense we can. Depends how we construct the representation space, of course, with the algorithm itself. But if we think about, there might be some overlapping notions between the tasks themselves. Sure, there's a lot of interference, but it makes sense that the tasks within the sequence have somewhat similarity. Otherwise, the whole continual learning project sort of breaks down. So, right, if we've already learned, a self-driving car has learned how to drive in one city with good and bad weather and snow, and you put it to drive in the countryside, well, in principle, it should kind of learn something from scratch, but it might still have this notion of how different weather conditions might impact, braking times or something like that. So I think that is something we can leverage.
Okay, thank you. I'm satisfied with the answers. Thank you.
Thank you, Professor Miloš. Then I would like to give the word to Professor Wang.
Thanks. Dear candidates, I enjoy reading your thesis. I also learn a lot of things from that. Particularly like the idea of test continual learning, because this I think is one of the promised direction for next phase of AGI. And also you extend it to the multi-agent system. I think is certainly very novel. And also I look at it, you already try to solve those problems by provide several baselines, which is definitely very interesting and promising. So I have the following two questions. Number one, in fact, not only you, but also there's other research group moving on, testing out, building up benchmark for continual learning. Like, for example, ARC AGI 3. I'm not sure whether you heard of it. I just want you maybe give a bit of comments in terms of compare the differences and also maybe you thought about what would be the best benchmark for continual learning. And related to that is whether that large language model might play some role in continual learning.
Hooggeleerde opponent, bedankt voor uw vraag. Yeah, this is a good thing to discuss because there's these two divergent paths in some sense. This agentic AI trying to also solve similar problems that reinforcement learning tries to solve. So I think there's two ways to think about it. One is the problem-solving aspect, and another is the benchmark and its usability itself. So from the perspective of the problem-solving, then, well, many of these reinforcement learning, the problems in the reinforcement learning benchmarks might be rendered too simplistic for the ones used in the AGI ones, and perhaps vice versa, it would be too difficult. But I think the key difference is when we talk about a reinforcement learning benchmark, then a big focus is also the training aspect of it. Not only that we have this giant pre-trained model that we now downstream try to evaluate what it can and cannot achieve. With the reinforcement learning benchmarks, the goal is also to see how good is the sample efficiency. What is the behavior during training? How well does it explore? So then we would want the problems in the environments to also facilitate that to some extent. So we can kind of pinpoint and zoom in what is going on under that lens. With foundation models, the core aspect of benchmarks is, well, here's a complex problem. Can it solve it? Can it reason about it? To what extent can it solve it? But the training part, that's already been done, most of the cases. There can be scenarios where we allow some fine-tuning. There are some discrepancies there, but I would say the core difference is this aspect of what happens during the lifetime of the training of the RL agent. And then, well, for the foundation models, it's just zero shot. What are they able to solve?
Do you think that there's some convergence between these two? Because I can see, for example, can you hear me? Can you see the convergence between these two? So in other words, that
we cannot hear you. Maybe you're muted.
It's better. Can you hear me now? Hello. Can you hear me now? Okay. I think other people can hear me. Is that okay? Maybe there's some technical issue. Oh.
There seems to be some technical
Control,
issue.
can you hear me, right?
Somebody step out. Maybe that will resolve it.
Yeah. People in the team then can hear me. Maybe I just type in. Okay. Is it better? Yeah. I guess maybe I just type my question then.
So I guess why behind the wall somebody's trying to sort out a technical issue. In the meantime, we'll maybe move.
Hello, can you hear me now? Uh-oh. Hello. Can you hear me? No.
In the room, but then yes, please continue, and then after that, sorry, Professor van Schoren, we'll move back to the room. Yes, Professor Wang, please go ahead.
Okay, can you hear me now?
Yes.
Okay, brilliant. Yeah, I just want to follow what the candidate said about these two dimensions. One is sort of AGI, large language model based way to do the pre-training, and then you do fine-tuning. And then you are that talking about the training and even maybe online training. But I can see that, in fact, there's some sort of convergence, right? That people are talking about test arm trainings. In other words, that when this large language model deployed, they still allow them to train, and people try to put effort. And this is what continual learning is really about. But obviously, in your case, you're looking at this IR case and talking about online learning. So I think that actually bring to the second question of mine, which is talking about sample complexity. So do you think, how can we solve this problem? Because if I look at this from a large language model perspective, because of the collection, maybe when people see a lot of progress in terms of coding, like for example, maybe you can ask the agent to write a code, and in the first few instances, they wouldn't work, but taking the feedback from the environment, then maybe the third time it works. So the sample complexity, I think, seems the large language model. So some sample complexity in certain aspect. So what do you think about in RL? Are we gonna bring some idea from large language model into it, or do you think there's other way to solve this sample complexity issue?
Thank you. I think that is a good thing to think about. So I wouldn't fully downplay the reinforcement learning algorithms here. I have seen some works where there's also relatively big model trains, say for robotics, and the task slightly changes, and they are able to, with maybe 5 to 10 scenarios where the robot tries to solve the problem and get some feedback, after only a few tries, it also learns to solve the task relatively well. Of course, you might say it's not too fair game because the reinforcement learning models still tend to be a couple of million parameters and in that range, whereas the foundation models are billions, if not hundreds. But also the representation space, I would say, is somewhat fundamentally different, because with the VLAs or the foundation models, there's also this notion of language directly, well, embedded, and there's this reasoning that we can track. With the RL scenario, we don't really have that. So I would say, well, on the one hand, there is definitely a sample complexity issue with reinforcement learning agents. They don't have this reasoning capability. They just learn and improve and adapt from a simple reward signal. And can we leverage something from that realm? Well, there can be some feedback loop that the RL agent has an opportunity to prompt something from a bigger model. For instance, I've seen some works on that. I wouldn't directly be able to propose what would be the way to close this sort of sample complexity gap here.
Mm-hmm. Yeah. Do you think the reasoning, has to be there or not? Because to me, I don't really see, because as long as you sort of training based on gradient descent, have this parameter, the gradient descent extremely efficient. And then you have to have thousands, if not millions of samples in order to get it work. But quite a lot of continual learning tasks that you need to have few examples and then, immediately learn from it. I mean, human doing that all the time. Do you think, in terms of solutions, that apart from reasoning, there's any other things?
I suppose the fundamental issue is the notion of exploration, and also it depends on what is the problem we're trying to solve. If it's again some robot trying to continually adapt to a very similar problem, but it hasn't experienced it before, then if we think about the action space, all the possible movements it can make with all the joints and actuators, then that is a very, combinatorially very large space. So by just, if we think about it from that way, then just by randomly trying something out, or at least not fully randomly, but leveraging what we've already learned, it is still a very big space to explore. With the VLAs, we can, in principle, solve similar problems, but there, I think the output space might slightly differ, that they don't directly output the exact minor, if we solve these control problems, that they don't directly output these very exact forces and torques of what the actuators should do to move the robot forward. But it's more of maybe a general output, and it's more hierarchical. I think perhaps that is a key distinction there.
Okay, good. Yeah, got you. Thanks. That's it from my side.
Thank you, Professor Wang, and apologies for the technical issues and inconvenience. We will again move back to the room where the opposition will be continued by the Secretary of the Committee, Professor Voshoor.
Thank you again. Dr. Wendes, I want to pick up on a variation of this idea. So instead of, let's keep using RL, but what if we replace the CNN encoder you use by a pre-trained VLA, for instance? Right, so since it's pre-trained a lot of data, it may have like a much deeper semantic understanding of physical spaces. And it's also very cheap to run on a laptop if you just do the encoding part. So do you expect that would change the nature of your benchmarks?
Zeer geëerde opponent, bedankt voor uw vraag. From what I've seen from past experience with these, even with these 3D benchmarks when we learn from pixel observations, the encoder does not play a very big role. The one that was designed from back in the Atari paper that had 3 layers of 64 units with very small kernels, often that is copy-pasted to a lot of projects, and it usually just works. Most of the cases. There can be always some fine-tuning to make it a bit better, but the core issue with RL is usually not the encoder, not changing the activation function, not adding a few more units or layers, but it's usually the feedback the agent gets from the environment, the reward signal, and the aspect of exploration and the policy updating and all those issues. So if we swap out these encoders for something more powerful, then given even that the inference time or the training time doesn't increase much and we don't focus on that, then hypothetically we could solve some more complex problems. Maybe we can scale up the resolution of these environments, because normally, however big the observation is itself, we scale it down to maybe something of 64 by 64 or a very small number of pixels compared to what VLAs are used to deal with, which is more of the real world. So potentially, if there are some more minor details that we would lose if we scale down, then well, we could have this high resolution when we learn.
Thank you. Do you think it would also help to generalize from the pixelized or 2D grid models to more realistic benchmarks?
Potentially, yes. Not generalize in the sense that we learn from the simplistic one and then we scale up, but if we immediately train on the more complex scenarios, not scaling down the observation space, then there is a possibility there. But I wouldn't bet too much money on that, because again, how we update the algorithm itself, the core issues are not usually learning the representations.
Okay.
It's unless we separate that, but generally it is more of this exploration and not getting stuck in local minima and all the deadly triad we have in RL that are the bigger problem.
All right, cool. So then let's switch to the reward functions. So for instance, in Hazard, it aggregates basically all safety costs into a single scalar, right? While in the real world, there's a big difference between just dropping a box or running into a human. So how would your baselines handle like a multi-constrained hazard where those costs are much differently prioritized?
That's a good point. Indeed, in neither cracks or hazard, we focused on multiple constraints. It is a planned potential extension, especially the cracks. There, of course, are works that have done this previously that have multi-constrained scenarios. And the same baselines I've used have also been used, because these are maybe not the most released in the past 1 year or two, but they are the most well-known ones. And they've also been evaluated in these multi-constraint scenarios. The question still is, of course, if we use the environments that I built and I sort of decompose these cost signals, I would say there's a bit of engineering effort there, and also like how, for instance, with the Lagrangian methods, now you have two costs to satisfy. So I would just have two Lagrangian lambdas that determine how safe you want to be for each. I think that would be a plausible approach. And of course, it would most likely lengthen the training times, but I wouldn't see why they wouldn't solve it, like to solve such scenarios. The question is, of course, if we keep scaling this up and we have 3 or 4 or more, then it becomes definitely more complex. Yeah, but in principle, should still be capable.
Great. And so linked to this, so VLAs also have language understanding. So would that help you to design like new constraint formulations where through natural language people can describe their priorities or constraints more naturally?
Mm-hmm. Yep. There's also quite some work that has been done by that. I even collaborated on a project where we did something similar. So indeed, it works if we also use natural language for that. Whether we can have a sort of a mix of natural language plus the constraint signal, then I'm not sure how they should be mixed. So I think either it's the raw cost signal that the environments currently give, or it is a textual signal that says in some way to because now the model should have some language input. So then it's able to receive from the environment something about the cost, something about safety, and now there can also be some guiding mechanism, maybe a human supervisor that types something that's something you have done is improper. And then in principle, if we have proper encoding, we use some bigger model that has already learned something about language, and then we use whatever embedding that gives us to replace this raw cost signal, then in principle we can achieve similar results, I would say. How much they vary, I couldn't comment on.
Yes.
But yeah.
Wonderful, thanks. So one observation you made was that sequence lengths master significantly, and I think that's still today, even how big you make those models. So with Coom, you used mostly 8 task sequences. In Meal, you had 100 task sequences, right? So do you suspect the conclusions you draw from Coom about the ranking of the methods would change or invert if you test them on longer, like 800 task sequences?
Yes, that is highly probable. That was, well, Coom was chronologically preceded Meal. So also one of the things that have always stood out in continual RL papers is simply how short the test sequences are. So that was one of the motivation to move on to hardware acceleration for continual RL. And as in one experiment in the thesis, I also show how methods that have almost identical performance after 10 tasks, if you scale the tasks up to 100, they completely diverge. So indeed, the results in Coom and the results in most of the continual RL papers that preceded it are questionable to the degree that indeed, if we scale up the number of tasks, do these results hold? The question is, of course, what is the problem we're trying to solve, right? Because sometimes we don't want to solve 100 tasks. Sometimes we know in advance that, well, there's not going to be more than 6 or 7 tasks. And then we only care about an algorithm that is able to indeed scale to that length. And then whatever happens after is not as crucial anymore.
Thank you. Is there more time?
A very brief question and a very short answer.
A very brief question. Okay. So if you were forced to deploy one of your train policies in your own kitchen tonight to prepare dinner for the Defense Committee, which agent would you use?
Sorry, again?
So if you were forced to use one of your train policies to cook a dinner for the committee, which agents would you use?
Well, I would simply take the one that had the best performance, which was the HAPPO agent combined with PACNet. Okay. That would be the chef of tonight.
Thank you, I'm satisfied.
Sounds great. Thank you, Professor van Schoren. Then I'll give the word to Professor Diaz-Simão.
Geachte promovendus. First of all, I want to congratulate you for the great work. I was impressed to see how many fields of reinforcement learning you actually cover on your thesis, and this is quite exciting to read about all of them. But yeah, I wanted to start asking you about one interesting aspect of one of your environments. So often you consider visual inputs for your agents. And in reinforcement learning, we have a very strong distinction between agents that can see everything about the environment, so they observe the true state of the environment, and sometimes they only observe a part of the environment, or there's a noisy observation. In hazard, for example, you actually have a visual input, right? So your agent cannot see everything about the environment. Now, all your algorithms actually assume that the environment is fully observable. And surprisingly, they actually perform quite well. Can you comment on what happened there and like how, what motivated this to happen?
Zeer geleerde opponent, bedankt voor de vraag. Indeed, it's a bit of surprising that in RL, sometimes things just work. So indeed, none of those baselines were particularly created for partial observability, and yet they are still able to solve it. I think, well, on the one hand, we just keep training the agent long enough that it sees very many sort of scenarios or transitions through the environment. The environment is not infinitely big. Like some of the ones I showed, there are like 4 walls and something around. So even though it's still partially observable and you never know what color wall is behind you, but because the environment doesn't change throughout this 500 million time steps that we trained through, then if the agent is in a particular location in the environment, then well, throughout these 500 million steps, it probably has been somewhere close to there. Maybe the exact same items or something else is not the exact same, but it has already had the opportunity to see likely scenarios, and it can kind of predict that if it looks slightly to the right, what might pop out of the corner.
I see. I'm curious if you have some ideas of how to extend now these environments that you propose to actually be able to also test then agents that require partial observability.
Agents that require partial observability.
Designed, let's say, for partially observable scenarios.
Right. So apart from the fact that, well, we only see a certain radius, we could obfuscate some part of the screen. There are many artificial ways of doing it that also is used in computer vision for making more generalizable agents. But for partial observability, also, we can make the environment a bit more stochastic in the sense. To some extent, it already is, but we can always scale that up and make more unpredictable things happen. So this is also something that we can consider a part of the environment or a part of the dynamics, so to say, of the environment, but it's not directly observed to the agent because it's only pixels. So the more we scale up the non-stationarity, I don't know, maybe the color of the sky changes after some number of steps. So, or it fluctuates even more. So by scaling such components, we can further induce partial observability.
Okay. I have a second question, and this is a bit more related to the field I work on safe reinforcement learning. And in this case, the main drive for the research we do is how to develop agents that actually satisfy the safety constraints, even during the learning process. So now I wonder, let's say we have a robot task, and we actually want to deploy these agents on the real robot. Do you think that your tools could help us to develop such agents? How we would go around to execute such tasks?
Yeah, thank you. So the safety during training is indeed not something the benchmark itself emphasizes. It is something we can observe from just the raw training curves itself, but there could be an extension towards that. In terms of deployment, well, I would say unless you want to turn the real world into the Doom game, then there is not too much chances to do about it. But so the environments weren't really designed for deployability, only to the extent that this mimicry of, well, navigating a 3D space.
Okay. But often we think about like transfer from sim to real, right? That could be one direction. Do you think your agents could, or your benchmarks could be adaptable to this kind of situations as well? So for example, we could model how the robot works and try to simulate it in cracks. Would that be feasible?
Yeah, with cracks, the chances are much greater. So then we no longer are in a video game environment, but there is physics guiding the agent, and we can roughly replicate that. I wouldn't say this, the Mujoko physics simulator is something that would do it that accurately, because our colleagues in mechanical engineering, are not too happy about the Mujoko environment because it's not hyper-realistic as well for their practical purposes. So I guess I would switch the simulator to begin with to be more certain about this potential for transferability. And well, then we need to think about what are the problems in the real world that we try to solve, right? So these ant agents, the ones you see flickering on the screen, they're most likely we don't have such in the real world. So we will probably need to recreate or find some 3D models that already have these agents pre-built that we then would want to, that would actually make sense to use in the real world.
Okay, that's clear.
In view of time, we unfortunately need to move on.
Okay.
Thank you, Professor Diaz-Simao. And then the next question will be asked by the co-promoter, Professor Fang.
Thank you. Yeah, congratulations. Thank you. And I read your thesis is very awesome. And I just have one question. So you did a lot in your systems, right? You at the beginning you developed DOM-based environments for reinforcement learning agents, and then you also considered extend it for safety issues, and then later you changed to use overcooked-based environments for multi-agent continuous learning. So a question is that what is the next, especially currently the large language model agents become popular, right? And like previous some professors mentioned that continuous learning, language learning. So what's your next for the benchmarks or the in the IO of the large language model agents?
Zeer geleerde opponent, bedankt voor uw vraag. So in terms of LLMs, I think for the time being, I will leave the majority of the LLM research to be done by the LLM researchers. But I think the next chapter would be a good opportunity to finally use and leverage these benchmarks that I've created to actually make something that uses them and to put my money where my mouth is to show that what they're actually capable of.
Thank you for the question. I'm satisfied.
Okay, there is still time available, so then we'll maybe move back to the previous opponent, Professor Diaz-Simao, who had a further question, I believe.
Yeah, so I'm very happy to be able to ask my last question. In SafeRL, we can think about this kind of constraints in many ways. So we could consider like soft constraints. So we are bounding the expectation over the sum of the costs. We can also have more hard constraints, as you mentioned on the thesis. I wanted to ask you, like, when you see the application of each of them and how your benchmarks can help us to make that more explicit to the user, for example, that these are actually different things.
So the gap is not too big because a soft constraint can be something very close to a hard constraint and it can be very far. So it's more of a spectrum, but I guess a hard means a flat zero of no safety violations. So I'm sure there are many real life scenarios that this would be crucial where, I don't know, we don't want a self-driving car to crash into a wall. So I think the applicability of this is evident. To what extent the environments can be used? Well, some of them, again, we can just set the safety bound to 0 every time, and that would inherently turn the problem into a hard constraint environment. Then the question is, do we only care about safety during deployment or also training? If we say hard constraint during training, well, then we get into this shielding methods, right? Where you don't even want to let the agent make mistakes or violate any constraints during training. So you predict the moment before it starts to do so, and then you pull the plug.
Can I ask if your methods or your benchmarks would be suitable for a shielding approach already, or how you can make them suitable? I see that can be quite challenging, actually. I wonder how you see this.
So I'm not too familiar with this line of work.
Yeah, the sound's
yeah,
back.
okay, we are back online. So yeah, in principle, again, there should be another extra model, some guiding mechanism that then learns up to, there's a window of steps that leads up to where the violation happens. Then we would need to train that model, whether we pre-train that or whether we do it in parallel end to end. And then it should, or we just collect some offline data and then train it separately. And then we can use that as a guiding factor to then train our agents that we want to have 0 violations during training.
Okay. I have a more broad question now, if I have the time.
Definitely.
Okay, so one key thing that is like lots of benchmarks were developed in your thesis, and the significance of benchmarking can be very seen in very different ways. What is your opinion on that?
Thank you. I kindly request that the candidate and his seconds return to their seats in the room. Then the meeting is adjourned and the committee will withdraw for deliberation.
I call this game Guess That Conference. If you think you have what it takes, guess that conference. Scan this QR code. Oh, I believe even the people online can take part in this great experience. I think we are limited to 50 participants, so I doubt we will get that many, but also we are limited with time a bit. So I'll wait a few more minutes. I think, can I use this mouse to zoom in? No. I think I'll wait for one more minute or until the count hits 50. So first come, first serve. You can also team up, leave spaces for others. Okay, is there still anyone attempting to scan, or do I have a green light to start? Yes, okay. Guess That Conference. A known game from the ages. We start with a little warm-up question. How many conferences have I attended in person? Having the lovely meal on China Eastern, I believe. Four. Oh. Well, sorry to disappoint. Four, indeed. It has been four. Let's see who were the four people who got it right, or five. Mahdi takes the lead. So, now to the game itself. Guess That Conference. This is me, Bram, and Gotham presenting Bram's paper, Muddy. Not to be confused with Mahdi, who currently holds the first place. Amos at Auckland. Wow, 10 of you. Not bad. Dr. Oh, I didn't know I was playing. It's a little nice foreshadowing. Guess That Conference. huge array of people. If you have very, very good eyesight, you can see at the very front, there actually is the acronym. ICLR, we got a majority vote. And everyone thought I wouldn't put two of the same answers in a row. Kuhn has taken the lead. Yes, that conference. When was Olama popular? Oh, wow, okay. Not bad. Very impressive. Kuhn still stands strong with Marco close behind. Is Marco here? No. Oh, there he is. This is me vehemently giving a presentation of Yu Cheng's paper, who had two conferences simultaneously and couldn't make it to this one. But luckily, I was up every... Okay. No. I was up 4 a.m. every night anyway because of the jet lag, so I had ample opportunity to prepare some nice slides to present Yu Cheng's paper. Brum has taken the lead. Yes, that conference. So this might not be at the conference venue itself, but closely after the conference as one of the socials. Singapore, ICLR, is correct. Oh, we have a new leader. Yes, that conference. I guess this is a hard one. If you know all about Bloomberg's doing at which expo it has set up its stage. Okay, that's surprising. There was very little information included, which is the correct answer in this one. Aurélien still stands strong. Guess that conference. I don't know how well you can see the screen. It's a bit, now that the lights are on, it's a bit hard to see, right? Amos. Oh, the technical support heard my plea. Thank you, thank you. Guess that conference. This is a famous photo taken by Brum and posted on Twitter, back when it was still Twitter. And then Jan LeCun reposted it on his Twitter, and it blew up, of course. Jan LeCun is a famous deep RL researcher. Nice, there we go. Who got it correct? Nice, Lika has risen into the top 3. Guess that conference. This is me with a humanoid drinking free bubble tea. I think if you have medium eyesight, this one wasn't too hard. Some people are guessing random or didn't notice what was under their nose. I wish, yeah. Posters graveyard. So with very good eyesight, again, on the posters, you could spot part of the acronym. Very good. Brum has taken the lead. I will speed up the middle parts a bit. I'm afraid to run out of time. This one is another example where a test of attention, whether you're clicking randomly or not. Nice. Beautiful. Who was the fastest? Brum is still leading. Guess that conference. One of our beloved ex-colleagues, 2 ex-colleagues, indeed. One of them is even here. New Orleans. What comes next? Oh, one of the papers in my thesis being presented. There is the logo of the conference on the top right side of corner of the poster, if you have very good eyesight. Okay, there's a draw between. I think people think Amos because we haven't seen an Amos question recently. Okay. I think if you've been to the city, you know exactly which one it is. Nice. Bram is standing strong. Okay. The lion dance. Okay, everyone knows. Okay, Lika is climbing close to Bram. Yes, that conference. So this is me on the left with Pascal on the right, pulled on the stage during the gala dinner of one of the conferences, performing this tribal dance in front of 300 people. I was at Amos. And Bram was laughing in the audience. At least Bram got it right. who took the video itself. The famous boat me, Udi, and Kuhn went on. I think one of the fanciest socials we've been on, with an open bar, a casino, free food, and a live jazz band on a 3-story steamboat. Yes, this was on the Mississippi River. I think Singapore, I would not be wearing so many layers because it was 30 degrees all the time. We have 3 more. This conference had a de-stress zone where they had freshly born puppies, I think 2 weeks old. They were mostly sleeping, but you can go there, get in the queue, and de-stress by petting the puppies. Yes, ICML. Okay, Liga has a chance. Kuhn is close behind. 2 more. Okay. Me and one of my lovely secondaries today. It's not at the conference venue itself, but indeed on the streets of New Orleans. Okay, goes in the top 5. And the final one. Guess that conference. This is at a workshop at one of the conferences. Vancouver. Well, we got a good distribution of answers. So, drum roll. Lika at 3rd place. 2nd place goes to Kuhn. And the winner of today, who guessed that conference, is Bram. Give it up for Bram, one of my secondaries. Congrats and thanks. Cool quiz. Appreciate it. Well, now there's only one thing left to do, and wait. I will erase all evidence before the committee comes in, and I think we are good.
I now have I hereby reopen the meeting of this doctorate committee and kindly request the doctoral candidate and his seconds to take their place in front of this table. The doctorate board of Eindhoven University of Technology, represented by us, has examined your dissertation and heard your defense of it. On the grounds of the aforementioned, the doctorate board has decided to award you the degree of doctor. I request that the promoter acquits himself of the duties entrusted to him, and for that we will all rise, please.
Uiteraard van bevoegdheid ons toegekend door de wil en namens het college voor promoties bewoordig ik u, Tristan Tamilin, tot dokter. En verleek ik u de rechten die verbonden zijn aan de dokterstitel. Ten bewijze hiervan overhandig ik u het diploma, ondertekend door de rector magnificus en de promotoren. Dear Dr. Tamilin, dear Tristan, it's a great pleasure to address you, first time as a doctor, on behalf of his monk and me. You've been within our group for a while. You did your master in Eindhoven with our department, and you did master thesis under supervision of Monk. You did really, really well. You already started to work on deep reinforcement learning. You looked into challenges of benchmarking. Your results were amazing, and we were extremely happy that you considered continuing with a PhD and decided to do so. Today, you presented excellent work and defended it also in a very strong way. Your work was praised by committee members, and you already saw some results of your work being appreciated by reviewers, by conferences, by many participants, and some people already start using the results of your work. And indeed, most of the chapters of your thesis have been published in the top machine learning venues, AI venues. The road towards that was not very smooth. Like, as every PhD project, yours had ups and downs. And I think you did an amazing job also reflecting in your thesis how the journey was. And it's not just about reviewer number 2 criticizing your work, or program chairs deciding to override the decision of PC members and area chairs, and eventually deciding not to accept the paper, even though everyone else would argue for that. It's also about finding out what PhD is, what PhD journey is, and what particularly your own journey in it. And I think you did a really amazing job, not just content-wise, but also experience in this journey. And I think in many ways it's also a role model for others, how to think and how to walk this path. And there were many bright moments regarding the content. It's about the joy of paper being accepted to a very competitive venue. It's also a joy of collaboration. It's a joy of seeing your results being appreciated by others and making first impact in a research community. Of course, there are many things also that goes next to science, next to PhD trajectory. I think you also did exemplary work of how diverse the life of PhD candidate could be. So it's not only helicopter flights, jumping from very high parts to the very bottom of something and going back, luckily. So it was quite adventurous in many regards. But you visited many places as part of conference trips and your other travel. You met many new people. You developed your professional network. You collaborated with more than 20 co-authors, colleagues. You've been invited to visit a few places thanks to amazing work that you did. So you also gave invited talks. You spent some time with research visits. But it was not only on professional side, it was also like being exposed to different cultures and learning from it. And perhaps one example corresponds to some of the comments we heard today, that you are quite direct. You don't hesitate to push back. And some of it comes through professional experience, like being part of different debates. Part of it is like fighting back reviewer number 2 and standing for your position. But part of it is also immersed into Dutch culture and being direct and saying like what you stand for and sharing your opinions and thoughts. And it also helps you to project confidence in what you do and move forward despite of some of the setbacks. You contributed a lot to research community in different roles. Your thesis itself serves research community by developing new tools to move this research area forward. It wasn't appreciated much in the past. I'm really glad that now it's been appreciated much more within community with different initiatives, also development of, for instance, benchmarks and datasets tracks, and its recent repositioning into evaluation as a science. And Hoffman-Horen is one of the advocates to such change as well. Of course, it also takes lots of courage and lots of push to advocate for what you do. And here I think you still can learn some bit or two from one of your paronyms, who is amazing in publicizing the results of research and making others aware of it. And I think it's quite important because your work indeed has lots of impact potential. And it's amazing when you see that other people use it not only through citations, but also once going to a conference and you see in a presentation or in a poster that someone was using your environment to report on their progress, it's nice. And I think there is much more potential to make your work to be known in a wide research community. You also served as a reviewer to major AI conferences and events, and on a couple of occasions you won an award as a best reviewer. In a couple of occasions it also helped you to win scholarships to attend conferences and then gain some other recognitions. As mentioned, your work becomes more and more appreciated. I'm really glad that you've already been invited to stay in different places, to give invited talks, and to spread the word about what you have achieved. And there are many things that I could say on personal side. It was really amazing experience to have you as a PhD candidate, to have you as a team member. It was pleasant in many regards and rewarding experience in many regards. It's a very important milestone. Of course, we wish you all the best with your future career. And we are glad that for now you decided to stay with us during the postdoc position. So we look forward for many more achievements and fruitful collaboration. Congratulations, all the best.
Thank you. Esteemed young Dr. Tomlin, on behalf of the doctorate board of the university, I also like to congratulate you with the degree. And the degree of doctor has rights as well as obligations, and let me read them out to you. As a holder of this degree, you are committed to standards of scientific integrity, trustworthiness, intellectual honesty, openness, independence, and societal responsibility. These standards are described in more detail in the Netherlands Code of Conduct for Research Integrity and in the Eindhoven Code based on it. You also have duties towards society. You must be clear about the boundaries of your own expertise, and you must communicate honestly and independently about the results of your work, including potential risks associated with it. You are committed to the ethical codes for research and design involving human subjects or animals. So these are serious words, and of course it is a very serious matter, but today is a joyful moment, and it's a real pleasure for me to congratulate you once again with your very successful thesis defense. And I hope that you and your family members and friends and colleagues will have a very enjoyable rest of the day and also a special meal tonight, if I understand it right. I would now like to ask you and your seconds to return to the seats in the room. So I'm about to close the meeting, but I would like to explain a few logistical things first. So immediately after I close, a photograph will be taken, and the photographer will assist us with that so that the online committee members will also be visible on the screen. And then Tristan, the young doctor, will have an opportunity to maybe exchange a few brief words with the online committee members as well. And after that, the beadle will sort of guide the committee outside the room, and there we will then sort of further do the congratulations. So with that, I will close the meeting.
Professor Milos, Professor Wang, thank you very much for taking the time to review the thesis. I very much enjoyed the discussion today, and I also hope to meet you one day, perhaps for some collaborations. And thank you, Mung, of course. I'm sad you didn't make it here today because of the visa issue, but yeah, perhaps I'll come to UK sometime. Okay, thank you.
Yes.
Cheers, cheers. Welcome. Enjoy.
Bye-bye.